You're listening to The Audit, presented by IT Audit Labs. Thanks for joining us, and welcome to today's episode of The Audit, where we will be discussing classical computing and what will be shaking up the industry beyond 2030. Join us on a journey with IT Audit Labs' own Bill Harris to learn more about the future of semiconductors, advances in lithographies, and what comes after silicon. You're not going to want to miss a moment of this information-packed episode, so make sure to listen until the end. You can stay up to date on the latest cybersecurity topics by giving us a like and a follow on our socials and subscribing on Apple, Spotify, or wherever you source your podcasts. More information can be found on itauditlabs.com. Well, we are here today to talk about the future of computing resources, or I guess the future of compute. And we've got Bill Harris joining us. So thanks, Bill, for coming on and putting together this presentation. I've had the chance to hear it one time before, and it's really awesome. So thank you for doing that. And this is part of a three-part series where you're talking about quantum and then the future of storage as well in other podcasts. And we've got Alan Green with us. So welcome, Alan. And Alan, you are from where?
I'm from a company called Fair Isaac Corporation, more lovingly referred to these days as FICO. We are known for your FICO credit score in the market, right? But we do more than that. We also sell software. And my role is I'm Senior Director of Infrastructure for the software division. And so I own that responsibility globally.
Awesome. So as an employee there, do you have the ability to adjust your score a little bit? How's that work?
I wish I could. But they keep me far away from the data.
Gotcha. And then we've got Nick Melamon, a regular here, hosting the podcast with us. So thanks, Nick.
Yes, sir. Happy to be here.
We're going to learn some stuff today. And Nick, Bill, Alan, and I go back a little ways from a previous organization that we all used to collectively work at, named Thomson Reuters. And Alan and Bill, did you guys spend much time working together? Or were you in kind of different divisions?
Well, we were in different divisions. You know, Bill had the sweet spot in the architecture space, and I was more so on the operations side, but we absolutely interacted.
And a little bit afterwards, too. Yep.
Yeah, admittedly, yes.
And you guys share a common hobby. And Alan, I saw you drinking from a red Solo cup. What was in that, Alan?
Iced tea, my friend. Just a little iced tea to keep the pipes well lubricated for the conversation today.
Otherwise known as bourbon. And Bill, you're a aficionado as well, are you not?
I am. And 2 nights ago, I had one of the worst Manhattans that I've had in Manhattan. So if you go to a show on Broadway and you go pony up to the bar, don't trust what they're going to put in that drink. It's they're not well trained. They really aren't.
Was it something off the rail? What was it?
No, they put in too many bitters. So I watched the guy, put in like a dash or two of bitters. I watched this guy dumping 8 to 10 dashes. So it didn't come out right.
And Nick, are you a bourbon guy also?
I am. And I would say I'm pretty strict to only drinking old fashioned. So I'm understanding what Bill's saying with the bitters. Gotta be careful with that.
Awesome. Well, we'll leave Alan to his tea, and let's jump into this this presentation. Bill, you want to give us a little backstory on this? How you got started, how you put this together, and then take us through it. It's pretty exciting.
Sure. So in my field, one of the things that I focus on is futures, technology futures. I've got a pedigree in storage and compute, so I found it pretty easy to latch onto these things and focus on what's coming up in the future. And I don't really care too much about the software aspect of it. So really, I'm more concerned about the hardware and the physics behind it. So consequently, I've had opportunities to connect with some of the advanced labs people from IBM, from EMC, from HP, some of the biggest companies. And I've been able to visit their advanced labs. and talk with the scientists behind this stuff and pick their brains a little bit from a non-product perspective about what's coming up and how it's going to shake the industry. For me, that's really interesting, and that's why I'm here today, is to share it with everyone else. So for today's agenda, I'm going to talk about the future of compute from current day up until around the mid-2030s. Our agenda will be in 5 parts. First, I'm going to introduce everyone to compute foundries, where these chips are fabricated, what the challenges are today, and what we're doing about those challenges. It's important to understand where the processors are made, and from that we'll get a better understanding as to what's coming up. We'll talk a bit also about what makes a processor better. So getting beyond those foundries, what are the scientists doing today to improve processor speeds, processor yields, and keep things competitive in the decade ahead? That will necessarily lead us into a conversation around the processor design and some of the constraints that we have to deal with, as well as how we're overcoming some of those constraints. And we'll talk about some of the innovative things that are getting introduced to processor design today and in the near future. We'll also talk about the physics and the chemistry that go into the processors. So it's not just a matter of how these things are assembled, but right down at the atomic level. What are the physics of today's modern processors? Talk about substrates, talk about lithographies, talk about the elements that are employed to build processors now and in the future, alternative elements that they're looking at. And then we'll wrap it all up and we'll talk about really kind of what this means for the industry and what we might expect to see in terms of some of those benefits and some of the challenges that lie ahead. So first off, we'll discuss about where the processors are made. And it's important to start here as we look at the five big foundries. Now, 90% of the world's processors are made in these 5 foundries. First up is TSMC, that is a Taiwan Semiconductor Manufacturing Company. And that's, as the name implies, it's based in Taiwan, and they produce 54% of the world's microprocessors today, from AMD, Apple, NVIDIA, other types that are in there. The number 2 is second, which is Samsung at about 17%. This is a South Korean company, and they develop processors for NVIDIA, for IBM most notably. UMC is number 3, also a Taiwanese company, producing processors for Texas Instruments and Realtek. UMC is about 7%. And they're tied with Global Foundries, which was founded in 2008 or 2009 by AMD, and then subsequently spun off. AMD wanted the capital, and they also wanted to focus really on being a fabless company. So AMD used that capital to really great effect, but now Global Foundries exist independently, and they're the only major foundry base here in the United States. They produce processors still for AMD and for Qualcomm. And then rounding out the top 5 is SMIC. This is the first Chinese entry, and they produce processors for Qualcomm, Texas Instruments, and Broadcom, among others. So you might see the problem here. As you look at these 5 foundries, the issue is that 4 of them, and approximately 83% or so, are based in Asia. So that creates a problem because any type of political or financial issue in Asia will affect worldwide supply. And that has national security implications. It has implications for the world stock markets and so on. It's just a lot of risk to have in one place, especially when you consider the strife that's happening between China and Taiwan right now. So in an effort to ameliorate some of that, the Biden administration introduced in 2022 the CHIPS Act, which encourages companies to build fabrications here in the United States, and it will subsidize their efforts to do that. So consequently, a number of companies have stepped up on that. TSMC is building a fab in Arizona, Intel in Ohio, and Micron is looking at New York. So building some of those processor factories here in the U.S. I think will help stabilize some of the risk that would otherwise be present.
Bill, in the top 5 there, I don't see Intel. I know you say they're building one out in Ohio, but where are those manufactured today?
So I think, if I'm not mistaken, I think Intel has one in New York, but Intel's not in the top 5, right? So they're working with other foundries here to produce.
So, and when you say chips, it's any of the processors that we might see on a motherboard or in a phone or in a car, or just the hundreds of thousands of areas that these chips could be in. And as I understand it, you could have a device that has chips from multiple different manufacturers. That's kind of the IoT problem, right? So you could have chips from all of these different foundries in one device.
Yeah, absolutely. Yeah, the term chips here really covers the whole gamut. Because when we think about processors today, we might think about the stuff that's in our computer, and that's actually, in today's world, a minority of the processors that are out there. You correctly named all the ones in your phones and the one in your refrigerator, and the one you have in your doorbell, and so on. It's just a ton of stuff out there. And so this presentation will really kind of talk about all of them, but it'll be focusing more on sort of the higher end processors, the types that you see in enterprise spaces for the most part.
So, Bill, I had been led to believe that the reason most of these chips manufacturers were in that region was due to 2 factors. The product required to build the chips was abundant there, and labor was inexpensive. Can you comment on whether or not that's factual?
Yeah, well, I think it is factual. I think the labor certainly is inexpensive, and that'll probably be your number one reason. Number 2, to an extent, as far as the product being readily available there, yes, the product is available there. It's also, when you talk about fabrication labs, it's a very sticky thing too. So once you have the infrastructure in those places, that's going to be kind of where you tend to continue to put it. With that said, though, and I'm going to get to this in just a moment, we're going to talk about silicon and just how abundant silicon is. So you're going to be able to find silicon, which is really the primary ingredient in these processors, being enormously abundant across the world. But yeah, I would say that what you're saying there is generally true, but that doesn't rule out from putting it any other place.
Okay, thank you.
Yep. So I want to talk a bit about how scientists today are improving CPUs over time. And when I talk about a CPU, literally speaking, the central processing unit, the main processor that gets things done, including any subprocessors, your ARM chips, your FPGAs, etc. It really kind of includes all of this. First and foremost, they're trying to make them smaller. And this is done for a number of reasons. First of all, smaller CPUs really just cost less in terms of materials. They also generally draw less power. You need to feed a smaller CPU usually a little bit less voltage than you do for a larger one because you're trying to push the electrons a shorter distance. They tend to produce a little bit less heat, and they're certainly going to result in a lot less latency, again because of those speed of light issues as you're firing electrons down the path. Important to stay here that when we're talking about smaller lithographies, you may see some of the manufacturers talk about, well, we've got a 7 nanometer process or a 5 nanometer process. These are not comparable among manufacturers directly. So these have really become marketing terms. So for example, Intel's 10 nanometer process fits 100 million transistors into 1 square centimeter. TSMC's 7 nanometer process does about the same thing. So there's just a difference in how they're building those lithographies that results in that type of a sort of this nuance in the way that they name them. Now, looking beyond just the reduction in lithography and making things smaller, I also want to point out that Moore's law, as has become pretty famous at this point about how every 2 years the number of transistors on a microchip will double, still lives. Its death has been touted for a while now, for several years, I think, but it kind of keeps pushing on and kind of going past the next level. I think it's got another couple years ahead of it yet before we'll have to reevaluate that for reasons that will become apparent. In addition to just reducing the processor to get the benefits that I just talked about, one of which is to get less latency out of it, I also want to point out that by and large, processor clock speeds have plateaued. And this happened like 15, 18 years ago at this point, where it started to kind of creep up around that 5 gigahertz mark and has roughly stabilized around that area. And that is just because as things have become a lot smaller, pushing things much over that has just produced a lot of heat and a lot of other problems that we'll talk about later about the way that electrons flow through the silicon. It's become problematic as it runs a whole lot faster. Interestingly, the speed crown for today belongs to an Intel Core i9-13900K. On liquid nitrogen, they've got that to run at about 9 gigahertz. Not particularly practical in the real world. Most residential applications are not going to be cooling with liquid nitrogen, and you'll find it in some enterprise applications, but there are risks associated with liquid nitrogen, including leaks. It's expensive. It's kind of dangerous. So it's not really a practical solution. It's just an interesting thing, but you generally won't see things go much higher than, say, 6 gigahertz or so via conventional cooling methods. And then finally, I want to call out, in addition to the densities and the clock speeds and the latency, one of the other things that they've done to push processor technology forward is to play clever tricks in it. So one of the things they can do is to improve the number of instructions per clock. Most modern processors today can do multiple instructions per clock. So it's not just one. Instruction sets also matter a lot, and you'll see these in today's processors in the form of SSL acceleration, in the form of AES 256 acceleration, in which you have a specific instruction set on that processor, calculate the cryptographic math necessary to encrypt and decrypt something like AES. Or similarly, you'll see instruction sets on modern processors that are really focused on virtualization, right? So they can hook into some of the Hyper-V calls or some of the VMware calls and accelerate those functions.
Where would be a real-world example of that AES type of encryption or decryption?
Well, it's in pretty much all the modern processors today. So AES is pervasive, to say the least, today. So nearly every modern proc today can handle that if you have an enterprise array or even a hard drive at home that you want to encrypt with, say, BitLocker or some other method. You'll find that the speed at which that processor can handle that encryption is a whole lot faster than, say some other types of encryption that it may not have an instruction set for. So there's a lot of use cases for it. I think as people become increasingly aware of security and privacy concerns around their data, and they're beginning to encrypt it more and more. And then assembly is also going to matter a great deal, and I'll talk about that on the very next slide, where I'll get into how they build these processors in innovative ways that really start to kind of stretch the limits of what we've seen. So in terms of assembly, it used to be that they would focus, like scientists would focus on the processor from end to end, right? There would be an X and a Y axis. And that was difficult enough. When we're talking about circuits at the microscopic level, and there are billions of them, that's kind of a difficult feat. But they've gotten so good at this, and their fabrication techniques have become so precise that they're now able to build up the chip more and more. We're seeing this in things like 3D NAND. A lot's been talked about with 3D NAND, and the reason that 3D NAND has become so dense is because they're now taking that into that third dimension. And they're building up the chip, and they're stacking these NAND layers on top of one another. So now, instead of getting, say, maybe like 16 gigabyte NAND chip, you're able to get up into terabytes of size.
What's NAND?
Oh, this is the flash. This is the type of storage that you use in your flash drives.
Oh, okay.
Interestingly, most NAND is also produced in Asia, so that'll be another conversation. But the way that this applies now to the processor design, and I'll give you a good use case on this one, is AMD has introduced in its previous generation and now into its current generation of what they call the 3DX chip, or the X3D chip, in which they're putting cache, a significant amount of cache, right on top of the main processor. And this has enormous benefits in workloads that can really use cache. So this is for workloads that tend to recall the same information over and over and over again. So it doesn't have to go all the way back out to main system memory. It just grabs it from the cache that is now bountiful sitting on top of the proc. So it works more with gaming than it does with, say, like a completely random relational database. But gamers have really latched onto this because they can get a whole lot more frames per second in their games, and and that's now driven, I think, more investment in the gaming industry with the likes of NVIDIA and ATI. So that's really been a boon to the performance of these chips. Another trick that engineers are putting into their processors is around chiplets, and so chiplets is a very specific chip or a wafer that is designed to perform a specific function, and you can generally produce these at greater scale because they do one thing, and they do one thing really well. Think of it as like just a very specialized chip, and you can put chiplets together to form bigger processors. And so you'll find chiplets now in a lot of the world's leading processors, and they kind of come together to do something bigger. Chiplets also give you a better yield because they are simple. The manufacturers end up throwing fewer and fewer of them away because they tend to come out right the first time. And then finally, it's a little bit of a tweak on some of the specific instruction sets I talked about, but building processors for accelerated workloads. And one of those is getting a lot of press recently is artificial intelligence. So as an example of this, IBM introduced their Telum chip on the Z16 mainframe. The Telum chip is an expert with AI inferencing, and it does that workload exceptionally well. In most use cases, it'll rival or it'll beat GPU computing for artificial intelligence. It's purpose-built to do that, and so it's really, really fast. We're actually seeing a lot of these types of innovations on big mainframe and supercomputers before they leak down into the smaller microcomputer segments. It would be a mistake to think that mainframes are old or somehow, dinosaurs, because that's not the case at all. We're seeing a lot of performance there and a lot of really cool things happening in that space. So it's a very innovative platform.
Bill, I know we're going a little bit down the rabbit hole here on the chips and the design, but maybe we could just back up for a second and talk about these specialized workloads. So you had mentioned GPU, which would be the graphical processors that we see on gaming chips, and one of those companies that's in the news recently is NVIDIA for making those graphic cards. And it sounds like there's an AI play using those cards, which is why the stock has taken off a little bit recently. But how do those specialized workloads, sometimes when we think of a chip, kind of looks the same, but how is the chip designed to handle one type of workload versus another?
So all of the chips work with a system underneath of it. It's not just a series of just meaningless circuits kind of banded together. So it works with the motherboard, and it works with the chipset underneath of it to employ a language. And the processor and the chipset come together to build that language that can be customized to those specific workloads. And that's the language in there, the machine language in there that has instruction sets built for very specific workloads. Some of the instructions can then short circuit, in a good way, short circuit some of the components in the chip. So for example, instead of one of the routines having to go to the chip and ask for a memory fetch, and the chip has to go to its registers and figure out where that data is, one of the instructions can be, well, for this particular workload, you don't have to go through that whole process. You can just go directly to memory because I know where that data resides.
You can use it in like IoT, like Alexa could have something cached, or Siri.
Right. Absolutely. Yep. Absolutely. It's great. It has great uses for things like IoT. So what I just described there was direct memory access. So it's those types of workloads that allow some routines to bypass a complicated mess of circuitry to accelerate what it needs to have done.
It used to be, going back a couple of years, when the Bitcoin mining or coin mining started, you'd have your spare PC at home and you could dedicate that to mining Bitcoins, for example, which essentially is solving a complicated math problem and trying to do it faster than other computers are doing it that are connected on the internet. And then I think somewhere it pivoted maybe 8 years or 9 years ago to GPU-based processing, because that was faster than the typical CPU of a computer to mine those coins. And now I think there's even more of a specialized miner that you can buy that people put into mining farms. I think one of them is a Dragon Mint. It's the name of the unit, but it seems that's the specialized workload that you're talking about, and that computer wouldn't be good for word processing or even gaming because it's so focused or specialized on just coin mining.
That's right. That's a good example. Other examples that I'll get into in a future conversation will be quantum. Quantum is good at extremely specific things and nothing more. Quantum is a lousy solution for a general purpose compute solution, but you give it a particular algorithm and it can churn through that one algorithm more quickly than anything else in the world can. So yeah, those are all good examples. So now we get to the semiconductor. So really what sits at the foundation of our processors today is silicon. Silicon is the second most abundant element on the Earth's surface. The first one is oxygen. And being so abundant, it is very cheap to gather. It's one of the non-metal elements, and it's a very good conductor and an insulator at room temperature. So that's what makes a semiconductor. Is you apply voltage, and you can make it a conductor or a or an insulator. Now we're going to continue to see silicon through this decade easily and into 2030. But I'll talk a bit about what happens at the end of this decade, the sheer mass of silicon and how much we are dependent on it today. It means it's going to be around for a while, and we really perfected it. However, some problems appear on the horizon. Silicon is really approaching the minimum size that we can deal with it within a processor type of a construct. So a silicon atom itself is 0.2 nanometers or 2 angstroms. A few years ago, 7 nanometers was approaching what a lot of folks thought would be the limit. But then came extreme ultraviolet radiation, and they were able to build silicon at even smaller lithographies and make it even more and more dense. So that will continue, and we're going to see this getting shrunk down farther and farther. Silicon will probably be deployed at 1 nanometer in the next 2 to 3 years. And at that size, you see that the silicon atom itself is just it's 0.2 nanometers. So it's really kind of getting down to really the smallest that it could possibly get, since it's at a 1 nanometer deployment. Now, the problem is at that size, silicon becomes susceptible to quantum tunneling. And quantum tunneling is a phenomenon in which a particle with insufficient energy can still pass through material that it shouldn't be able to pass through by the laws of classical physics. And of course, that's a major issue for something that is supposed to be highly predictable and that has to be 100% correct. And so that's really, they will have to overcome that problem, I think, before they can really shrink it down much further than 1 nanometer.
Nick, we're getting pretty deep in here.
Yeah, some of this stuff is, the one thing that was hitting me too was the marketing from a couple slides ago. Like how Apple keeps talking about, oh, now our chips are, 7 nanometers, I think was the 8, 13 or whatever. So there's so much stuff here that I was not aware of that we can unpack. But yeah, we're getting really deep.
And Bill, I certainly can understand shrinking the chip down to use less energy, make it more efficient, less heat. And I can certainly appreciate that for memory, making cache bigger, which would be on-chip memory, or instead of like a hard drive, right? It's just maybe a different form of having it becomes denser, so we can store more data on it, right?
Mm-hmm.
I get that, but when you said, I think was it maybe 8 or 9 years ago, where we reached the maximum speed of like 4 gigahertz on a chip, and we think about our common business use case application of a PC or a laptop or a MacBook, how much smaller does it really need to get? Like, does a 7 millimeter or a 10 millimeter chipset really make that much of a difference when I'm running iOS or Windows or Mac OS or whatever it is? Like, we're just doing Word and surfing the internet. How important really is that dense chip?
Doesn't it just become a heat thing at that point, Bill? Right? The smaller, then it just gives off less heat, right? So it can be fanless. Maybe?
Yeah. So all that plays into it. I would argue that if you're just surfing the internet and you're looking up recipes and sharing cat pictures on Facebook, that you don't need the most modern processor. You don't need miniaturization. You could actually run a fairly just a typical processor with barely a fan. The reason that we're seeing miniaturizations continue in processor design is they want to squeeze in more transistors into that die, because more transistors mean more execution units, and that means they can just shove through more work through that processor. So that's Moore's law, and so you'll continue to see that miniaturization drive those big workloads that we talked about earlier: artificial intelligence, deep learning, machine learning, data analysis. All that's very important for those things, but you won't need that. Most people won't need that for their home PC. You're not really going to need that so much for IoT, unless you're trying to miniaturize the device itself, and then you need everything inside of it, including the proc, to be miniaturized. So a lot of things go into that.
So what you're saying, Bill, is if you need it, you know you need it. If you think you need it, you probably don't. You're probably good with the normal chip.
Yeah, I think so. Absolutely. I think that's very true. If you really need it, you'll know.
Right.
So we talked about what happens when silicon reaches that 1 nanometer level, and we start to run into some problems with classical physics, and we start to see some limitations there. So what comes next after silicon? How are engineers, how are scientists looking to overcome those barriers? So they have introduced into the labs a bunch of solutions that absolutely work, which includes new semiconductors. There's a whole list, and this is a partial list here, but a lot of this really focuses around different forms of elements and doping one element with another element. So silicon carbide is silicon that's doped with carbon. There are other carbon semiconductors listed here: diamond, graphene, graphene, all carbon-based. And these, like I said, these exist in the lab today, but not in a method that is able to be mass produced in any type of an economical fashion. So the race is on. The race is on to find the replacement to silicon in a commercially viable, mass reproducible way. It's important to note that not all of these semiconductors are used units are built of elements that are smaller than silicon. However, they are almost all of them more conductive than silicon, which means less energy is lost to heat. They also consume less power, which is going to be huge as we go into, to a more environmentally conscious world. After this, I'll talk more about what's happening in superconductivity, but this is what we're looking at right now in terms of semiconductivity, and this will probably start to take place, towards the end of this decade. But I don't think you're going to see any of it really get perfected until early to mid 2030s.
Bill, could you maybe talk a little bit about where copper might come in? Because I'm picturing a circuit board, and I'm picturing copper kind of interweaved within the green board itself, and then chips and resistors and transistors and whatnot on the board. But where's that relationship between like copper, and then where does silicon come in?
Mm-hmm. So copper is a conductor. It is a great conductor of electricity, and so that's what it's going to do. It's always going to conduct electricity. So you'll see copper used for lines that are supposed to just be always carrying electricity, always carrying a signal of some kind, whereas silicon will be switching off and on between being an insulator and a conductor.
It's like I wish I paid more attention in that 8th grade electronics class now, Nick.
I've been thinking that the whole presentation.
So this is where things get really interesting, right? So after semiconductivity, really I think the holy grail of where computing is going for the foreseeable future is superconductivity. So the graphic that I'm showing you here in the upper right of this screen is, of course, it's a very recognizable one, the Large Hadron Collider in Switzerland, which is
hold on a second, Bill.
Yeah.
Nick, did you know what that was?
Well, I was coming off mute to ask. Never seen this.
Oh, okay. Okay. Then
I like how Bill's casual. He's like, yeah, everybody recognizes this, right? We should just start showing Bill pictures of different stuff.
I recognize it.
I've clearly had my head in this for way too long then. All right. So
we'll have to see if you can recognize the difference between two different breeds of cats that Nick has.
So this is in CERN, Switzerland, and it's just a giant machine. It's miles and miles long, and they've been using this to test superconductivity and quantum mechanics. So in superconductivity, all energy passes without resistance, and nothing gets lost to heat, which is huge. We've talked about heat a lot. We've talked about the loss of energy. If you can make all that go away, then you've got yourself something really special. Now, the superconductivity is nothing new. The Dutch discovered superconductivity in 1911. They were experimenting with mercury and liquid helium. Again, two things you should not find in readily available in anyone's home, but we've known about it for a long time. And in recent decades, we've begun to sort of envision some of the commercial applications for this. Problem with superconductivity, though, as you can maybe guess from the liquid helium element up there, is that in order for it to work, you need one of two things. You need either very high pressure, or you need to be very, very cold. And by cold, we're talking about absolute zero cold, or as near to it as you can get. We can do this today, and as I'll talk later on, we've done it with quantum computing. Quantum computer is a superconductor. It does all of its operations at approximately the temperature of space, but it takes a lot of energy to get those types of temperatures or that type of pressure. And so it becomes a little bit of a sort of a catch-22. Is you can get superconductivity, which kind of loses nothing to heat, but you have to spend a lot of energy just to get it cold enough to even do that. So the scientists are searching for solutions at a normal atmospheric pressure or something at room temperature. Needless to say, that is going to be very difficult to do. And if they find it, good luck reproducing it. We're probably a few decades, maybe 4 or 5 decades away from really being able to do that. I think you'll probably see some breakthroughs on it, but much like the recent breakthrough we saw in cold fusion, it's going to take quite some time for that to really come around and mean anything. However, when it does, when it happens, it will absolutely revolutionize electronics. And here's how it's going to do that. We talked about some of the consumer grade processors, enterprise grade processors today, which is a chip, maybe 2 inches square, a few millimeters high. And around that chip sits all kinds of cooling apparatus. You might have big fans. You might have liquid cooling with radiators. Anywhere from 2 to 5 pounds of cooling material to cool this little tiny device. And all those fans and all that liquid cooling draws power, and it takes up space, and it costs money to produce. With superconductivity, if we could get there, that goes away. Now all you have is the chip. No longer do you require all that extraneous stuff around it. So yields can increase. You can use less materials. You're not producing heat. You don't need as much air conditioning in your data centers. You can run your data centers like almost like a normal room. You don't need giant chillers, big water pumps flowing through. So it would truly shake the industry when this ever comes about.
You could get that PUE right at 1, couldn't you?
Yeah, yes. To use those data center terms, absolutely. Your efficiency would be at 1. Yep.
Now, if we continue to nerd out a little bit here with Bill, Nick, I kind of think everybody should have their own favorite physicist, and mine's Brian Cox. So Brian Cox is a physicist. He works at CERN in Switzerland, and he's got a couple of YouTube videos that I think are particularly cool. One of them is called "Why We Need the Explorers," and he did it's a TED Talk. It's on YouTube now, but it was a TED Talk, and then he did another one on CERN's Super Collider. So if you want to see some of the stuff in action, Bill, I would surmise it's going to be on this particular TED Talk. But the Why We Need the Explorers is about the spending that countries have on science education, and Brian talks about the Voyager mission, where Voyager is now reaching the edges of our solar system, and had been sending pictures back along the way, and one of those pictures shows Earth as just a tiny speck of dust, and I think it's a pretty eloquent passage that he reads about that particular picture. But I was on a long flight, I think it was to London one time, and I was watching these TED Talk videos and came across Brian, and subsequently watched him and Dr. Miku Kaku, who's also a physicist, and talks about different technologies and things like that are pretty interesting. But anyway, I went down even more of a rabbit hole, so I'm going to turn it back to you, Bill.
Those are all good
Nick's
rabbit
laughing.
holes. Yeah, I know those two physicists. They're a lot of fun to watch. Yep. So to start to wrap all this up, what does it all mean, right? So I want to be clear that silicon isn't headed out anytime soon. It's going to be around a long time. It's sticky stuff. I think it'll be around until 2030, and it'll be around after that. But around that time, I think we're probably going to see some innovative elements come to the forefront. I also think we're going to continue to see some really cool things in processor design. We're seeing it from, I think, seeing some especially innovative things, mostly from like IBM, NVIDIA. Intel's lost a little bit of their shine recently, I think, but they still got it in them, and I think they still introduced innovative things, and I think they're gonna come back and continue to do that. Overall, though, I think in order to shrink semiconductors past their current state, and into the 2030s, you're gonna need to have new stuff. We're not going to be able to get that much more out of silicon. Just the physics for it, it's just not there. We're going to reach other barriers when some of the gate sizes within those processors reach a single atom. We can't do anything with it at that point. We can't shrink that any further than one atom. So it's going to become really interesting at that point, which will probably be in the mid-2030s or pushing into the 2040s. And I also want to be clear too that although quantum computing is getting a lot of press, as it should be, it's not going to address any of this because quantum computing is designed at very specific workloads. It is not a replacement for a general purpose computing device. It's not a replacement for IoT. It's none of that. It's something else, which I'll get into at another time. But classical computing will continue to drive our information age, but we will have to find new substances to take it into the next era.
So how do we make money on this, Bill? What's the stock market play with this stuff?
Well, if you have yourself a few billion, you can hire the engineers and some plants to build some of the stuff. This is one of those areas where it's really hard to break into. This isn't like software, where you can write clever software and you can do it from your garage. Yeah, this is stuff that huge organizations will have to drive, and I think the barrier to entry here is really high indeed.
Bill, can you go back? I think it was 2 slides. Switzerland. How big is this? I think you mentioned it, but I'm just...
Oh, it's miles long. Miles and miles long, yeah.
And how big is, like, top to bottom here, do we know? It just looks giant, so I was curious.
Yes. It is, I want to say, and I might be wrong on this, but I want to say it's probably around 30 to 50 feet across or something to that effect.
Wow.
Yeah. Yeah, if you see, I'm not sure if you can see my mouse come across this screen here, but you can kind of get a feeling for the scale for this platform work to the left.
Oh yeah, I didn't notice that before. Yeah,
I believe you can tour it too if you happen to be in Switzerland at the time they're allowing tours, which I don't think is all of the time, but I know that it is open.
I wasn't aware of this. It's really cool.
This superconducting particle collider got a lot of press when it was opened. What was it, maybe 15, 20 years ago, I think it was. My history is a little rusty on this one. But it got a lot of attention because there was a fear that it would create a black hole that would destroy the Earth and everything around it. And I think at the time, something like 98 or 99% of the world's physicists said, no, that's definitely not going to happen. But it's always that holdout. It's always like that one dentist who doesn't like the same toothpaste that all the other dentists like. What if that one's right? And so there was always this fear when this thing opened that it would just result in our complete obliteration.
I thought they were paid by the toothpaste companies to like certain toothpaste.
Probably. I'm not sure who's paying the scientists though to speak out against this.
Well, yeah, there's certainly a lot of information here. I think, we spend so much time trying to secure software and tools and, help end users be better, but it's really cool to see kind of how the light bulb is created and what we're actually securing from a holistic level. I've never been this deep, with what we're talking about, so it's really cool to learn all these different items that go into it.
Cool.
Can we ask you a couple other questions, Bill?
You can. I will warn you, I am not a physicist. I'm not a chemist. So this is, we'll see how, I do have my limits, but go for it.
Is the Earth flat?
Oh boy.
Yeah, that's one of those
There you
things where if you have to ask, you're not going to like my answer.
go, Bill.
So that's not a yes or a no, Nick. We didn't get that out of him.
Okay.
I don't think we have enough time to unpack that one.
And then the last question is, how long have you been a brony?
What is a brony?
We just learned about this last week, I think.
But a brony is a person who collects My Little Ponies.
Really? Really? That's a thing.
True.
Okay. Well, 5.5 years then. Yeah, I'm going on my 6-year anniversary.
Gotta be honest.
Yeah.
Cool. Well, Bill, thank you. This awesome presentation. Learned a ton, and it sounds like you've got. What's up next? Is it quantum or is it storage?
Quantum. Quantum's next, and
Quantum.
then storage.
And the storage, we're going to get into things like using DNA or crystals for storage, something like that,
We'll
right?
talk about crystalline, molecular storage, DNA storage, all of that. Yep, all of which exists today in the lab. It's all proven technology.
It's crazy.
I feel like I've got to do some reading before I'm even ready for that presentation.
Don't come too prepared, please. I'm sorry, what was that?
I got to brush up on my favorite physicists.
Oh, yeah.
Absolutely.
Yeah, that's right.
You have been listening to The Audit, presented by IT Audit Labs. We are experts at assessing security risk and compliance while providing administrative and technical controls to improve our clients' data security. Our threat assessments find the soft spots before the bad guys do, identifying likelihood and impact, while our security control assessments rank the level of maturity relative to the size of your organization.